All right, friends and neighbors, time to get back to some more networking, and we are going to continue with OSPF, or Open Shortest Path First. Now, I did a demo last time, but I suppose we ought to talk about some of the background and some of the basics of OSPF. So you're probably asking yourself, if you've never talked about routing protocols, what is OSPF? Well, hey, it's a routing protocol. So that means that we're not static routing. So a lot of times when we have a topology that doesn't change very much, or is a simple topology or a small topology, we use static routing. But the minute things get complex, we drop into dynamic routing. And when we say dynamic routing, we mean a routing protocol. So with a routing protocol, what you do is you simply turn them on the router, and the routing protocol itself figures out where all of the destination networks are. But because it's automated, that doesn't necessarily mean that it's perfect. So there are some oopses, some things that we have to adjust sometimes in a routing protocol. Now, when we talk about a routing protocol, there are really two parts to it. The first part is the protocol. It's what we see on the wire. So that includes the messaging, all the fields, the information that they're conveying, and all of that. The algorithm itself, whether we're talking about Bellman Ford or Dijkstra, is what happens with the data once you get it. So the router gets it, does a couple of calculations, and then figures out, based on the calculations and the information given, where the destination networks are, how far away they are, best pathways, and all of that. So remember that when a router is given information, what a router is trying to do is figure out if that information is better than the information it already knew. Now, it's pretty straightforward. If they've never seen that, they go, okay, cool, there's a network that I've never been to. I'll put that in my routing table. But if the router already has information in the routing table about that destination, it has to evaluate the information. And remember that there are three things that we worry about. The first one is prefix length. That is the length of the mask. And the longer the mask, the smaller the address space that we're talking about. So we could say that that's closer to the destination. So we prefer masks that are, longer, 24, 25, 26 bits in the subnet mask, as opposed to something like 8, 9, 10, 16, something of that sort. Assuming that the prefix lengths are even, then the next thing that we look at is admin distance. And admin distance is a measure of the quality of the route. And so directly connected is an admin distance of 0. Static is 1. And then you get into your routing protocol. So OSPF has an admin distance of 110, RIP has 120, and so on. If we're talking about two routes that have the same prefix length and the same admin distance, meaning they were learned via the same protocol, then we look at the metric. And the metric is an evaluation of the path to the destination, either how far away it is, or the speed of the links, or both. And so the metric is sort of the last stop. But we need to go through that process to determine if we're going to accept the new information. Now, before we go any farther into OSPF, let's talk a little bit about the traveling salesman problem. And this is the classic routing problem that we talk about. And so what I want you to do is imagine that you are a salesman and you're trying to get to all of these cities to make your sales. And so let's assume also that you have limited time maybe, or you want to minimize the travel, etc., etc. So you have to go through all of these cities. Well, you want to find the best pathway to all of those cities. That's part of it. But now imagine that you're trying to get to all of them. What is the best way to get to all of them from wherever you are? So remember that a router is trying to take a look at the network from its perspective. And so you're trying to develop this picture of how to get to all these destination networks from where you are. And then, of course, if you're a different router, you have a different perspective. And so if we try to get to all of these cities or all of these destination networks, what we're trying to figure out is, well, what's the fastest way there? What maybe is the shortest distance? Those are not necessarily the same thing. What pathway should I take that has the least amount of traffic? Now imagine that you're worried about a couple of these at the same time, or maybe all of them at the same time. So clearly the problem gets more and more difficult the more qualities we search for. And this sort of illustrates some of the differences between not only the algorithms, but some of the metrics associated with routing protocols. So for example, RIP, the routing information protocol, only cares about the pathway to the destination. In other words, it's that way and how far away it is. OSPF says, well, it's nice to know that it's that way and how far away, but wouldn't it also be nice to know about the speed of the links that we're going to travel over? So the different routing protocols have different considerations when they're trying to determine the best route. So let's just do the OSPF fact sheet. OSPF, like many of the routing protocols that we take a look at, is an interior routing protocol. So it's designed to be run by one administrative controlling agency. So at RIT, we have our interior routing protocols. Organizations have their interior routing protocols. This is as opposed to something like BGP, which runs on the internet. Clearly, it's a routing protocol, so it's router-based and dynamic. The algorithm that's behind this is a link state algorithm. So the routers are going to communicate to each other their states. This is as opposed to something like distance vector, which simply says, hey, it's that way and here's the magnitude of the distance. It's multipath, meaning that if there's two pathways and they have the same metric associated with them, we can load balance between them. We will also find out that OSPF uses a combination of broadcast, multicast, and unicast addresses to get the job done. It just depends on what the event is. It's hierarchical in the sense that the routers do different jobs. We'll talk about that here in a minute. Now, there are lots of different kinds of messages associated with OSPF. We'll do that in another video. The most common OSPF version that we talk about is OSPF version 2, and all of that can be found in RFC 2328. There are lots of other interior routing protocols, although today, probably the most common that you're going to run into are EIGRP and OSPF, with a smattering of ISIS out there. Operationally, OSPF runs in an autonomous system. So that administrative control thing that I was talking about, well, that is the autonomous system. The other operational idea is that routers within an OSPF autonomous system are trying to figure out their area topology. Now, as we can see in the graphic above there, you can have one area or you can have multiple areas. Whatever area you live in, your router's job is to find out your topology within that area. And the autonomous system collects all of the areas together. Areas have individual numbers, and no matter what, you have to have an area 0. That's the backbone area. All other areas interconnect via the backbone, but you got to have the backbone area. Now, within an area, the routers communicate to understand the topology within that area. And an area topology can be really complex with lots and lots of routers, or it can be very, very simple with just a few networks. Once that topology is discovered, that constitutes the area link state database. Routers actually communicate to each other using messages, and in those messages they're saying, hey, here is my state. Here are the networks and interfaces to which I am connected. That constitutes my state. By the way, here's some details about the links, and here's what I know. I'm going to tell you my state. And then together the routers will build a link state database. Now, the routers within an OSPF topology have different jobs. Within area 0, we have the backbone routers. Those are the ones labeled BR. Area border routers are the ones that sit, well, between two areas. So area border routers know information about two different areas. Because everybody interconnects via area 0, you're going to know about your area, say 51 here in this case, or 52, and the area 0. Area routers, or routers within an area, simply communicate with each other, and they know eventually what the area topology is, but anything that's got to go outside of their area, they don't really care. They just send it to the area border router. Now, there's another idea that we have to talk about when we start talking about routers and who they're willing to share information with. When we get to complex topologies, it may be that there are lots of routers that are communicating with each other. Now, neighbors are routers that share a connection to a network. and they're both doing OSPF. But the question is whether or not they're going to share routing information with each other. So they're neighbors if they're both doing OSPF and they're on the network. But if they share information with each other, then they establish what's called an adjacency. So it's possible to be a neighbor and not adjacent, but all routers that are adjacent are also neighbors. So in the example here, we've got area router 1 that has a connection to the area border router. And there are 2 other area routers there. And the back and forth arrows indicate that those routers want to establish adjacencies with AR1. But the 2 routers at the top there may not want to share information with each other. So there's no reason to establish an adjacency right there, although they would be neighbors, or they might be neighbors. Well, that'll do it for this video. This has been a gentle introduction to OSPF. So we talked a little bit about structure and the traveling salesman problem and some of this routing protocol's background. Now, OSPF is pretty complex. We'll try to hit some of the additional high points. So next up, we'll talk about messages and the operation, the ebb and flow of those messages. But in the meantime, thanks very much for watching. Thanks for listening. Like and subscribe if I helped, and may those packets always reach their destinations.